The difference between a comet and a national security threat should be simple. One is rock and ice, faithfully riding gravity's rails. The other demands classified analysis that can't be unpacked in public. So explain this. Why did 3I, Atlas, officially described by NASA as a natural comet, provoke a GLOMAR response from the Central Intelligence Agency? That's the legal posture used when even confirming or denying records would expose state secrets. Not we have nothing, not here's a blacked out file, but we can't even tell you whether we're looking. And if they aren't looking, the secrecy is absurd. If they are looking, we deserve to know why. Stay with me to the end. The answer isn't what you think. If you feel that same quiet pull into these questions, go ahead and like the video and subscribe so you don't miss what comes next, as this story keeps unfolding. Leave a comment telling me where you're watching from, what time it is in your corner of the world, and whether you think the official explanations are giving us the full picture of what's really happening up there. Part 1. The GLOMAR that broke the narrative. On December 31st, 1998, a document researcher named John Greenwald Jr. received a reply from the CIA that shouldn't exist in this context. He'd filed a Freedom of Information Act request about 3I Atlas, an interstellar object NASA had publicly waved off as nothing more than a comet passing through our solar system. The CIA could have simply answered that no records existed. They could have released heavily redacted pages with the interesting parts drowned in black ink. Instead, they issued what people in government recognize immediately, a GLOMAR response, a refusal to confirm or deny whether records even exist, because that single admission would reveal classified intelligence sources and methods. Let me be precise about what a GLOMAR response signals. This isn't paperwork hesitation. This isn't bureaucratic nerves. GLOMAR is reserved for matters sitting at the core of national security covert operations in hostile places. The identities of foreign assets. The technical reach of surveillance systems so sharp they could read the date on a coin from orbit. It's the shield the government raises when even acknowledging documents would compromise ongoing intelligence work, or expose how information is gathered in ways that can mean life or death in the field. And the CIA invoked Executive Order 13526, protecting intelligence sources and methods from public disclosure. That's the same executive order used to classify how we track nuclear programs, penetrate terrorist networks, and monitor foreign military communications, yet it was invoked for a comet. Now set that beside what happened 6 weeks earlier. On November 19th, 1998, when NASA held a press conference about 3I Atlas, NASA's scientists stood under lights and microphones and declared the object a natural interstellar comet, presenting spectroscopic readings, trajectory math, outgassing models, standard astronomy, carefully explained. No threat to Earth. They said, no properties that couldn't be accounted for by conventional astrophysics. The message was calm, almost soothing. We found a visitor. We studied it. We understand it. Everyone can return to ordinary life. A civil space agency built on scientific transparency treated this as routine cosmic business. A foreign intelligence agency built to protect secrets treated its very existence like classified material. One of these organizations is misrepresenting something, and I'm not sure which option is more unsettling. Here's what makes it especially strange. The CIA had an easy exit ramp. They could have said, plainly, that no records related to 3I Atlas exist in their files. That happens all the time with FOIA requests. Someone asks about a topic the agency truly never touched, and a polite letter comes back, sorry. We have nothing on that. Case closed. But they didn't take that path. They chose GLOMAR, which means they're protecting something. Either they have records they cannot acknowledge, or they're involved in activities tied to this object that remain active and operationally sensitive. The choice itself tells us the simple fact of files exist or files do not exist is classified intelligence information. Think about that. Not the content, just the existence. What kind of comet requires intelligence-level silence? What kind of drifting space rock becomes a matter that could compromise sources and methods meant to protect American national security? These aren't rhetorical fireworks meant to feed conspiracy. They're process questions, real ones. They're questions about how administrative machinery behaves and why two arms of the same federal government, looking at the same sky, arrived at opposite decisions about how that sky should be handled. NASA published, briefed, invited the public in. The CIA raised the same legal walls used for spy satellites and covert operations. This isn't, at its core, about whether 3I Atlas is natural or artificial. It's about why the government's response is split, why reassurance and secrecy occupy the same bureaucratic space while pointing in opposite directions. So, let's be clear about what we're doing here. This is not a hunt for proof of extraterrestrial intelligence. This is not an attempt to persuade you that aliens are visiting Earth. This is an examination of process, the mechanics of secrecy, and what happens when contradictions become too sharp to ignore. We're going to walk through the physical oddities associated with 3I Atlas, the statistical discomforts, the patterns that might mean everything or might mean nothing, but we'll do it with eyes open, separating what we can prove from what we can suspect and from what we simply cannot know because someone decided the public doesn't get access. The Glomar response is our starting point because it's the only part of this story that is unquestionably, documentably strange. Everything else requires interpretation, balancing evidence, weighing alternatives, resisting the urge to leap. But that CIA letter, that's weird no matter which way you turn it. And if the foundation is weird, maybe we should look carefully at what's been built on top of it. Part 2. The double-track government problem. Governments have always run on two tracks at once. There's a public track, press conferences, statements designed to preserve stability and prevent panic, and there's a classified track contingency planning for scenarios publicly described as unlikely. This isn't conspiracy, it's risk management. When you're responsible for millions of lives, the public gets reassurance. The classified apparatus gets worst-case possibilities. Both tracks can operate in good faith, serving different functions inside the same system. Understanding that dual reality matters if we're going to make sense of what's happening with 3I Atlas. Think about how many times early warning systems have detected what looked like incoming nuclear missiles only for human operators to realize it was geese. A glitch. Sunlight off clouds. Most of those near-miss moments never reach the public, because announcing them would spark panic or reveal technical details adversaries could exploit. But behind closed doors, protocols ignite, calls are placed, people move into predetermined positions, and the rest of us keep drinking coffee, unaware that for 15 minutes someone thought the world might end. Pandemic response offers another clean example of this same two-track approach. Public health agencies run tabletop exercises, simulating catastrophic outbreaks, lethal pathogens, societal fracture, mass casualties. Those exercises remain largely classified or restricted to narrow professional circles. Meanwhile, the same agencies speak publicly about readiness, robustness, and how unlikely the worst cases remain. Both tracks can be honest in their own way. The public track focuses on probable outcomes and maintaining trust. The classified track focuses on possible outcomes and preparing for failure modes. The contradiction only becomes visible when something forces both tracks into the same light at the same time. That brings us to black swan theory, why intelligent people can make decisions that look irrational around low-probability events. A black swan is outside normal expectations, carries extreme impact if it happens, and then gets explained afterward as if it was inevitable all along. The key idea is this for certain risks. Probability matters less than consequence. If something has a 1% chance, but would break civilization if it occurs, you don't treat it like other 1% risks. You treat it like an existential threat worth preparing for, regardless of how unlikely it seems. Intelligence agencies live in asymmetric downside. They don't ask only, is this likely, they ask, if it's real, can we survive being wrong? And that question changes everything about how information gets handled. So let's reframe the central question about 3I Atlas. We're not asking, is it alien? That's for scientists. Over time, through peer review and accumulated evidence, we're asking, is the downside asymmetric? Does this object carry a risk profile where being wrong has consequences so severe that normal probability instincts stop being useful? Intelligence agencies care about unknown intent, because intent is how neutral becomes hostile. They care about unknown capabilities, because capabilities turn theoretical threats into practical ones. They care about unknown timelines, because timing decides whether you have years to analyze or seconds to react. When you don't know what something is, you don't know what it might do. And when you don't know what it might do, you don't know when it might do it. That uncertainty forces a posture of maximum caution, even when it looks ridiculous to outsiders. And here's the distinction. Most people miss scientific certainty and intelligence. Uncertainty live in different worlds. Scientists build confidence through repeat observation, testable predictions, peer review, replication. They move carefully from hypothesis to theory to established fact. And that method is beautiful for understanding nature on human timescales. But intelligence analysis operates in another epistemological space. Analysts build confidence through pattern recognition, comparative casework, game theory, and assumed adversarial behavior. They move from incomplete information to actionable assessment because waiting for scientific certainty can mean waiting until it's too late to prevent what you're trying to prevent. Both approaches make sense in their domains. The problem arises when the same phenomenon demands both kinds of analysis at once. Why does the unlikely but catastrophic push governments towards secrecy? Because public discussion of catastrophic scenarios can create its own disaster markets wobble. Cohesion phrase. Adversaries gain leverage. Even preparing for a worst case can make that worst case more likely. So governments do what they've always done. They smile and reassure in public while building bunkers and running scenarios in private. That isn't necessarily cynical manipulation. It can be practical necessity in a world where information itself can be dangerous. The question isn't whether this dual track exists. The question is whether it's happening right now with 3i Atlas, and if it is, whether the secrecy is protective or whether it's covering institutional uncertainty and confusion. Let's connect this back to our interstellar visitor. 3i Atlas is interstellar, meaning it came from beyond our solar system. From a region we can't directly observe and can't control. It's non-repeating, meaning we get one chance to study it before it vanishes back into the dark. And it's not controllable, meaning if it does something unexpected, we have no way to stop it, redirect it, or mitigate what follows. Those three traits together create exactly the kind of risk profile intelligence agencies are built to worry about. Not because aliens are likely, but because the consequences of being wrong about aliens would be so profound that normal probability math stops being a comfortable guide. The public track says comet, because comet is the most likely explanation and the least socially disruptive one. The classified track says glomar, because even if it's probably a comet, the alternative possibilities carry such extreme downside that you treat it as national security until you're absolutely certain, and maybe not even then. But what if the physical evidence starts whispering that absolute certainty won't be available? What if the anomalies begin to stack? Part 3. The sunward jet that shouldn't exist. On December 30th, Downtinling Arshawu, astronomers with the Virtual Telescope project captured images of 3i Atlas that revealed something physically peculiar. The comet displayed what's called an anti-tail, a jet of material pointing toward the sun instead of away. If you remember anything from basic science, you remember this. Comet tails point away from the sun, pushed back by solar wind and radiation pressure, like quiet wind socks in space. It's the kind of rule you can verify with backyard telescopes. It's one of the first truths ancient skywatchers learned about those wandering fuzzy stars. So when you see material drifting sunward against the fundamental forces that usually govern comet behavior, you're seeing something that demands an explanation. Not just any explanation, but one that accounts for persistence, why this sunward jet remained visible before perihelion and after perihelion, holding its geometrically wrong direction across shifting distances and heat. The standard model argues that anti-tails can be optical illusions, a trick of viewing geometry, where dust left along the orbit appears as a forward-pointing tail from certain angles. That works in some cases. It explains classic anti-tail observations well enough, but it strains with 3i Atlas, because this sunward feature wasn't subtle, wasn't fleeting, and wasn't confined to a narrow window of perspective. Multiple observing campaigns from different locations captured it, and it persisted across changing solar distances and changing positions between Earth and the object. Thermal outgassing models, usually reliable at predicting comet behavior, couldn't neatly account for the intensity and directionality being reported. Something was pushing materials sunward with enough force to contend with radiation pressure, and with enough consistency to keep that direction across weeks. Which brings us to an uncomfortable comparison. In 2017, the first confirmed interstellar object, Oumuamua, showed non-gravitational acceleration as it left our solar system. It moved a little faster than gravity alone predicted, gaining speed without obvious outgassing like a normal comet. Scientists proposed natural explanations: hydrogen, outgassing too faint to detect, exotic ice sublimation, even rotation creating thrust through uneven solar heating. All of those ideas are plausible, probably correct. Certainly more likely than alternatives that demand a rewrite of celestial mechanics. But they share a feature: they explain a force without a clearly observed mechanism. We saw the acceleration. We didn't see what produced it. We saw the effect and inferred the cause. 3I Atlas feels similar. We see material moving sunward, but we don't directly see what's overpowering radiation pressure. We observe the effect, infer natural causes, and sometimes stretch our models in ways that make researchers uneasy while still insisting correctly. That unease is not impossibility. Discomfort isn't evidence. Physics is full of things that once looked impossible until the mechanism came into focus. Ball lightning, rogue waves, both were impossible until we learned the dynamics underneath. The universe is reliably stranger than our neatest models. And science advances by updating models when observations refuse to cooperate. So something unusual isn't automatically artificial, alien, or intelligent. It often just means our current framework handles it poorly, which happens constantly in astronomy. But here's where the intelligence angle enters. Unknown forces mean unpredictable behavior. If you can't predict behavior, you can't assess risk. And if you can't assess risk, you default to caution until you can. An intelligence analyst looking at 3I Atlas doesn't need the sunward jet to be alien. They don't even need it to be exotic. They only need one question answered: are the forces acting on this object understood well enough to predict what it might do next? And if the forces aren't understood, if the models are struggling, and the observations stay persistently odd in ways that resist clean explanation, then, in threat assessment terms, you're dealing with an unknown. Unknown forces can imply unknown control. Unknown control can imply unknown intent. And unknown intent is exactly what keeps intelligence agencies awake at night. I want to underline this, because it's easy to slide from "this is weird" straight into "therefore aliens," skipping the necessary steps in between. The sunward jet is weird. It's physically unusual in ways that challenge standard comet behavior models. Multiple teams have noted it, written about it, tried to reconcile observation with theory. But physically unusual is not the same as physically impossible, and physically impossible is not the same as artificially made. Nature does strange things constantly, often stranger than anything we could design, because nature has access to timescales, energies, and complexities that dwarf human engineering. So when scientists label something unusual, they aren't raising flags and shouting aliens. They're saying the models need refinement, that observation has once again outrun theory, that the universe has reminded us softly, relentlessly, how much we still don't know. The question worth asking isn't whether the sunward jet proves the object's origin, it's whether that anomaly, combined with other anomalies we'll examine, creates a pattern that shifts the probability landscape enough to justify unusual government attention. One weird detail is just astronomy being interesting. Several weird details clustering around the same object starts to look less like random coincidence and more like something deserving closer, quieter scrutiny, not because anomalies prove design, but because they hint our understanding may be incomplete in ways that matter. And if your job is assessing threats under incomplete understanding, you don't wait for completeness before taking it seriously. You take it seriously now, investigate discreetly, and hope quietly that when the data finally settles, It confirms the boring natural explanation everyone assumed at the start. But you don't wage a civilization on hope. You prepare for alternatives. Part 4. Geometry so clean it looks engineered. There's something unsettling about 3i Atlas's orientation in space, something that grows more unsettling the longer you hold it in your mind. Its rotation axis is aligned sunward within about 8 degrees. Its orbital plane is aligned with the ecliptic, the flat disk where Earth and the other planets travel within about 5 degrees. Before you shrug and think, so what, let me tell you why those numbers can feel wrong. Interstellar objects enter our solar system from essentially random directions in three-dimensional space. They aren't constrained to our preferred plane, and they aren't supposed to arrive politely oriented. They fall through the galaxy on whatever trajectory their last gravitational encounter delivered. The odds of arriving with a rotation axis pointing near our sun and an orbital plane matching the planetary plane aren't zero, but they're not comforting either. Think of it like this. Imagine standing in the center of an enormous empty field while someone a mile away throws a dart at you. Blindfolded, the dart has to travel through three-dimensional space, tumbling, arriving from any angle at all. Now imagine it arrives spinning exactly parallel to the ground, traveling exactly along the surface, no rise, no dip. You'd catch it and think, that's lucky. But you might also wonder if the thrower wasn't as blindfolded as they claimed. Because while chance can do it, aiming produces that result on purpose. The alignment doesn't prove aiming, but it makes aiming feel less absurd than it did before you caught the dart. 3. I-Atlas is that dart, arriving with sunward spin alignment, traveling close to our planetary plane, showing a kind of geometric cleanliness that would make perfect sense if someone planned it, and feels oddly convenient if nobody did. Multiple astronomers have noted the alignment, and to their credit, they've been careful not to oversell what it means. Alignment is not design. Random chance can create clustering, can paint a pattern where none exists. Flip a coin 1,000 times, and you'll get runs of 10 heads, purely by probability, even though any single run looks impossibly unlikely. So, geometric alignment doesn't automatically mean an intelligently guided object. It means something statistically improbable that may or may not carry deeper significance. But here's where statistics get sharp. Each alignment alone is unlikely, but not shocking. Maybe the sunward rotation axis is around a 1 in 5 kind of happenstance, and the ecliptic alignment around 1 in 3 6. Those are small probabilities. But in a universe with countless interstellar visitors, you'd expect a few. The tension appears when you multiply them together. Ask for both alignments in the same object, and you drift into odds more like 1 in 1. Bye-bye. And while that's still possible, it's enough to make you pause. Then you add the sunward jet. The chemical signature we'll discuss next. The signal alignment we'll cover later, stacking improbabilities until random chance starts to feel less like a conclusion and more like a question. And that gentle stacking, more than any single oddity, is what statisticians call clustering. And it's both the most powerful tool we have for detecting real patterns, and the most dangerous for tricking us into seeing patterns that aren't there. The human brain is a pattern recognition machine, evolved to spot the tiger in the grass, and to assign significance to randomness, because missing a real threat has always outweighed the cost of mistaking wind for teeth. So we're predisposed to connect dots and build narratives that make coincidence feel like connection. Sometimes that instinct serves us, guiding us to real phenomena buried in the noise. And sometimes it leads us astray, building elaborate theories about forces and intentions that live only in the quiet theater of the mind. The challenge is separating those two cases, pattern versus pareidolia, especially when the stakes are high. Navigation convenience matters in risk analysis because convenience can suggest optimization. Natural processes don't optimize for human observation or human accessibility. They don't care whether we can study them easily, predict them cleanly, or feel reassured by tidy explanations. Engineered systems do optimize, because engineering is about reaching specific goals efficiently. If you were designing a probe to tour our solar system efficiently, you'd launch it into the ecliptic plane, where the planets already travel. If you wanted to maximize time spent near the sun for power generation or data collection, you'd orient key systems sunward and let the star sit like a steady lantern in your field of view. The geometric configuration of 3I, Atlas is, on paper, the configuration you'd choose if you were optimizing for those goals. That doesn't mean it was optimized. It means the geometry is consistent with optimization in a way that pure random arrival is not. And that opens a distinction between peer review caution and classified worst-case modeling, one that explains some of the disconnect between what scientists say publicly and what intelligence agencies may be considering. Privately, scientists publish conservative interpretations because their reputation depends on being right, on not making extraordinary claims without extraordinary evidence, on avoiding the slow embarrassment of being corrected by better data. That caution is admirable. It's also necessary, a kind of scientific gravity that keeps speculation from floating away. But it also means published papers tend to understate uncertainty, favor conventional explanations, and resist speculation that can't be definitively supported. Intelligence analysts don't face the same constraints. Their job isn't to convince peer reviewers or win elegant arguments. Their job is to prevent disasters. So, they can and must consider low-probability scenarios that scientists would never put in a paper. Because the cost of dismissing a real threat can be vastly higher than the cost of investigating a false alarm. When you see clean geometry, when you see statistical clustering that makes professional astronomers reach for words like unusual, unexpected, requires further investigation. You're seeing science do what it does best: publish careful papers, propose follow-up observations, and maintain appropriate skepticism. But you might also be seeing something intelligence agencies handle very differently by running classified assessments, gaming out scenarios, and asking not what's most likely, but what's most dangerous if we're wrong. The Glomar response suggests exactly that posture, treating 3I, Atlas, as something that warrants intelligence-level analysis, rather than purely scientific analysis conducted in daylight. And the geometric alignment provides at least one reason why they might have made that choice. One anomaly is an anomaly. Multiple anomalies begin to look like a pattern, and patterns, even patterns that might be purely coincidental, demand investigation when the stakes are high enough. We're still in the realm of questions, but we're not done stacking improbabilities yet, because the chemistry has its own oddity. Part F, the nickel problem. When astronomers point spectrographs at comets, they're taking chemical fingerprints, reading which elements are present and in what proportions. It's the same principle that tells us what distant stars are made of. It's also the same technique that can reveal the composition of alien atmospheres light years away. For comets, we expect a fairly standard chemical signature: lots of water ice, carbon compounds, silicates, and various metals in trace amounts. The ratios shift depending on where in the galaxy the comet formed and what kind of stellar environment shaped it. But there's a broad pattern most comets tend to follow. 3I, Atlas follows that pattern mostly. With one notable exception, the nickel-to-iron ratio is off. Not wildly off. Not impossibly off, just enough to make spectroscopists pause, double-check their instruments, and sit with the uneasy feeling that they might be seeing something a bit unusual. Nickel is common in the universe. It forms naturally in stellar cores and supernovae, scatters into the interstellar medium, and becomes part of planets, asteroids, and comets as solar systems form. So, finding nickel in a comet is completely expected, exactly what our understanding of stellar nucleosynthesis and planetary formation predicts. The question isn't whether nickel should be there. The question is how much nickel relative to iron, because that ratio tells us about formation environment, temperature, history, and the slow sequence of processes that concentrated some elements while depleting others across the object's long, cold journey. Comets formed in the frigid outer regions of star systems tend to carry one kind of ratio. Asteroids formed in hotter inner regions tend to carry another. The ratio is a clue to origin, pointing back toward where the material once lived. And this is where 3I, Atlas, becomes especially interesting, at least to those who live by numbers. The nickel-to-iron ratio reported for this object resembles ranges we associate with industrial alloys more than most natural bodies. Stainless steel, for example, contains nickel and iron in proportions that provide corrosion resistance and structural strength. Certain aerospace alloys use similar ratios for high temperature performance and low mass. To be absolutely clear, this does not mean 3i, Atlas is made of stainless steel or aerospace alloys. What it means is simpler and stranger. The naturally occurring ratio happens to fall within a range that humans have independently discovered to be useful for engineering purposes. This could be complete coincidence. A numerical overlap without any deeper story. Nature uses the same periodic table we do, follows the same chemical rules, and sometimes arrives at the same practical solutions when physical constraints push matter toward particular configurations. Still, it's worth thinking about why humans use these specific nickel-to-iron ratios in our alloys. We use them because they provide optimal performance for certain applications. Centuries of metallurgy refined our understanding of which proportions work best for which purposes. Nature doesn't optimize for human purposes. It doesn't care about corrosion resistance, tensile strength, or the engineering parameters that drive our choices about material composition. Nature only responds to pressure, heat, radiation, time forces that don't negotiate. Nature optimizes, if we can even call it that, for whatever environmental pressures exist in the formation region, pressures that rarely align with human engineering concerns. So, when you see a naturally occurring ratio that happens to match a human-optimized ratio, you're left with two broad options. Either it's coincidence, nature arriving at the same solution from a different path, for different reasons, or the optimization isn't coincidental. The ratio exists for the same reason it exists in human alloys, because someone chose it deliberately. Scientists, sensibly, flag anomalies without drawing conclusions, because drawing conclusions requires more evidence than a single unusual measurement can provide. Science works by accumulation, gathering data from multiple sources, testing hypotheses against independent observations, building confidence through replication and review. A single odd spectrum doesn't prove anything. It suggests a question worth investigating. Why does this object's chemistry differ from expectations? That question can be answered in a dozen ways, most of them purely natural, and all of them requiring further study before anyone can say with confidence what is actually happening. The scientific process is working exactly as it should. Note the anomaly, propose explanations, plan observations that can distinguish between competing hypotheses. From an intelligence perspective, though, the calculus is different. Industrial-like signals trigger attention not because they prove artificial origin, but because they present a signature that could indicate intelligence. Intelligence analysis operates on a simple rule: investigate signatures before you dismiss them. You don't wait for peer review certainty, because by the time you have certainty, you may have lost the only window to respond if the signature meant what you feared it might mean. So intelligence agencies see the nickel ratio, note that it resembles engineering choices, and factor that into their threat assessment models while still acknowledging it's probably natural, probably explained by formation chemistry we don't fully understand yet, and probably nothing to worry about in the long run. This highlights a fundamental difference in how scientists and intelligence agencies handle uncertainty. Scientists publish their uncertainties, debate them in journals, present them at conferences, and treat uncertainty as something to be resolved through more research. That is the right approach when your goal is understanding the universe when being wrong means updating your models and trying again. Intelligence agencies classify their uncertainties, discuss them in secure facilities, and treat uncertainty as something to be managed until resolution because they're not trying to understand the universe in general. They're trying to prevent specific bad outcomes. If that nickel ratio is natural, fine, no harm done by taking it seriously. If that nickel ratio is a hint of something engineered and you ignored it because it seemed unlikely, you've failed at your primary job function. The asymmetry of consequence forces an asymmetry of response. Act 1 has given us 4 distinct anomalies: the Glomar response that shouldn't exist for a natural comet, the sunward jet that resists easy explanation, the geometric alignment that seems too clean to be random, and now a chemical signature that resembles human engineering choices. None of these anomalies taken individually proves anything beyond the fact that 3i, Atlas, is an interesting object worthy of scientific attention, but taken together, They start to form something that looks like a pattern soft-edged, incomplete, yet hard to ignore. Not conclusive proof. Not smoking gun evidence, just a pattern, unusual enough that some people are paying very close attention while trying very hard not to say so publicly. The comet explanation fits most of what we observe. It fits incompletely, leaving gaps and questions, requiring assumptions about processes we haven't directly confirmed. Maybe those gaps will close as we gather more data. Maybe the questions will resolve into natural answers that make perfect sense in hindsight, the way mysteries often do after the last clue arrives. Or maybe the gaps are gaps for a reason, and the questions don't have natural answers. Either way, someone in government thinks this situation requires intelligence-level secrecy, and we haven't even gotten to the really weird part yet. Part 6. The WOW signal alignment nobody wanted. In August, Omianoa Sutashapta Zetshi Shapte, a radio telescope at Ohio State University detected something that should not have happened. For 72 seconds, a narrowband radio signal at exactly 420 megahertz blazed into the receiver, so strong and so precisely concentrated that astronomer Jerry Amon grabbed his pen, circled it on the printout, and wrote "WOW" in the margin. That exclamation became the name by which history knows this event. The WOW signal represented what SETI dreams of: a powerful narrowband transmission from one point in space. The kind an artificial transmitter would create, and nature rarely does. Multiple follow-up observations found nothing. The signal never repeated. Decades of analysis never conclusively explained it. Some researchers propose natural causes like hydrogen clouds or passing comets. Others suggest we genuinely detected an extraterrestrial transmission that we've never been lucky enough to catch again. The debate continues. What does a 48-year-old radio anomaly have to do with 3I, Atlas's sky position? When you plot where the WOW signal originated and where 3I, Atlas, passed through our solar system, they align within approximately 9 degrees of each other on the celestial sphere. Now, 9 degrees is not a perfect overlap. It's roughly 18 times the angular diameter of the full moon, a region of sky that contains thousands of stars and countless stretches of dark, empty space. But it's close enough that when researchers started noticing the alignment, they calculated the probability of coincidence. The estimate came back at approximately 0, Bifangelo. Not impossible, not even spectacularly unlikely, but unusual enough that dismissing it as pure chance takes a little faith in randomness. And let me be very clear about what correlation does and doesn't mean. Correlation is not connection. Two events happening in the same region of space, decades apart, could easily have nothing to do with each other. The universe is vast. Objects move through it constantly, and given enough observations of enough objects, you will eventually find alignments that look meaningful purely by accident. This is the multiple comparisons problem. It's the same reason studies testing 20 different hypotheses will find one statistically significant result just from random variation, even when no real effects exist. If you look for patterns hard enough and long enough, you'll find them. That doesn't make the patterns real, doesn't mean they point to underlying causes, and it doesn't justify building elaborate theories on what might be nothing more than cosmic coincidence. So why do intelligence agencies track correlated anomalies even when correlation doesn't prove causation? Because their job is pattern recognition in environments where patterns might indicate threats, where the cost of missing a real pattern vastly exceeds the cost of investigating a false one. They're not trying to publish papers or persuade skeptics or maintain academic credibility. They're trying to prevent bad outcomes by identifying threats early, while intervention is still possible. In that context, unusual coincidences get flagged for further investigation not because they prove anything, but because they suggest questions worth answering. If 3I, Atlas, has absolutely nothing to do with the WOW signal, fine, investigating costs time and money, and comes up empty. No real harm done. If there is a connection and you ignored it because it seemed unlikely, you've potentially missed the most significant discovery in human history until it was too late to do anything useful with that information. This introduces a fundamental tension in how we process unusual correlations. Pattern seeking is how humans discover real phenomena. Before we understood gravity, Newton noticed an apple falling and made a connection between that event and the moon's orbit. finding a pattern that seemed absurd to many contemporaries, but turned out to describe a fundamental force of nature. Pattern seeking gave us relativity, quantum mechanics, evolution, plate tectonics. Every major scientific breakthrough emerged from someone noticing correlations and asking whether they might indicate something deeper. But pattern seeking is also how humans fool themselves into seeing agency where none exists, meaning where there's only randomness. Conspiracy where there's only chaos. Every false conspiracy theory, every pseudo-scientific delusion, every paranoid fantasy starts with pattern seeking that doesn't know when to stop. The human danger is seeing meaning everywhere. We're wired to find faces in clouds, animals in constellations, intention in accidents. And this tendency served our ancestors well when survival meant erring on the side of caution, assuming the rustling grass might hide a predator even when it was usually just wind. But in the modern world, that hair-trigger pattern recognition can tempt us to construct elaborate narratives connecting dots that don't need connecting, finding significance in randomness because our brains don't rest easily with true randomness. The institutional danger is the opposite, ignoring rare convergence because convergence seems improbable. Large organizations develop cultures of skepticism that protect against conspiracy thinking and prevent resources from being wasted chasing phantoms. But those same cultures can make institutions slow to recognize real patterns, dismissive of unusual correlations, overly confident that what seems unlikely must be impossible. Why did the wow signal alignment enter this discussion at all if correlation doesn't mean connection? Because it's another improbability to stack on the pile. The sunward jet is weird. The geometric alignment is weird. The nickel ratio is weird. And now we learn this object passed through a region of sky that 48 years ago transmitted something so unusual that astronomers are still arguing about whether it was natural or artificial. None of these things individually proves that 3I, Atlas, is anything other than a comet. But collectively, they create a probability landscape where the pure coincidence explanation starts to strain a bit, not break. Just strain. And when intelligence agencies notice that strain, when coincidences start piling up in ways that feel less coincidental with each addition, they begin asking questions privately while maintaining public neutrality. There's one more piece on the board. One more reason the wow signal overlap was taken seriously enough to enter the 3I Atlas conversation. Even with all the obvious objections about correlation versus causation, we didn't just watch an object drift through that patch of sky. We watched an object with multiple oddities do it: curious geometry, unusual chemistry, persistent strange behavior passing through the same region where, decades ago, we caught a signal that still refuses to sit neatly inside any explanation. Stack enough improbabilities, and eventually you start to wonder, are you looking at a statistical hiccup or something more structured hiding inside the noise? You start to wonder whether someone should aim the most powerful instruments we have at this thing right now before it slips out of our solar system and becomes unreachable forever. You start to wonder whether anyone already did exactly that, and whether the results might help explain why the CIA chose a GLOMAR response. But those observations would have been looking for signals, which means we have to talk about what they found, or, more precisely, what they say they didn't find. Part 7. Radio silence isn't exoneration. In December 2025, the Breakthrough Listen project released results from an observation campaign targeting 3I Atlas. They aimed some of the most sensitive radio telescopes humanity has ever built at the object and listened across a wide span, roughly 1 GHz to 12 GHz, covering the bands where artificial transmitters would most plausibly operate. If artificial transmitters were operating, the listening window ran for about 5 hours, long enough to catch a steady beacon, and even periodic signals with short repetition times. They detected nothing, no narrowband transmissions, no structured pulses, no obvious modulation, nothing that read as technological. The quiet was total, and for many people, that silence settled it. No transmission means no machine. Case closed. Everyone can stop worrying about alien probes. But let's slow down and be precise about what that window actually rules out and what it doesn't. 5 hours, across that frequency range, rules out continuous, omnidirectional broadcasting in those bands during those 5 hours. That's not nothing. If 3i Atlas were transmitting non-stop in all directions like a cosmic radio station, we would have heard it. The fact that we didn't means either it wasn't broadcasting, or it was broadcasting in a way that didn't match our listening assumptions, and those assumptions are always limited. Because radio observation is expensive and time is finite, telescope time is precious. You can't monitor every frequency, in every direction, all the time. You make educated guesses where to look, when to look, what to look for, and then you run the observation and report what the data says. So, consider what negative results actually remove from the map. We can say with confidence that 3i Atlas isn't behaving like Voyager 1 or Voyager 2 human-made probes still crossing interstellar space. Those probes transmit continuously, sending data home in a broadly accessible way that any sufficiently sensitive receiver could detect. If 3i Atlas were doing something comparable, Breakthrough Listen almost certainly would have seen it. We can also rule out careless leakage, like the kind Earth produces TV broadcasts. Radar sweeps. Communication satellites, radio waves spilled into space as a side effect of not caring who might be listening. A civilization sloppy with its emissions tends to be detectable even when it isn't trying to communicate. So yes, the silence tells us something real. It tells us there's no careless broadcasting, no omnidirectional beacon, no obvious technological signature, at least not in a 5-hour slice across 10-ish gigahertz of spectrum. What it does not rule out is burst transmission. If 3i Atlas transmits in brief pulses instead of continuously, those pulses would have to happen while we were listening. Miss the window by an hour, and you miss the burst entirely. Humans use burst transmission in spaceflight all the time. Continuous transmission drains power. And continuous contact isn't necessary when you're millions of miles away. You wait until you have something to send. You wake the transmitter. You speak. You go quiet again. An object using the same logic might transmit once per orbit, once per day, once per hour. And if those moments don't overlap with our 5-hour watch, we hear nothing. The silence doesn't prove there's no capability. It only proves there was no detectable transmission during our window. Directional beaming offers another clean explanation for radio silence. Earth broadcasts broadly because we're not aiming at a single target in deep space. We're trying to reach receivers scattered around our own planet. But for interstellar distances, omnidirectional broadcasting is wasteful. You pour energy into every direction when you only need one. Directional beaming concentrates power into a narrow cone, making the signal blindingly strong where it's aimed and effectively invisible everywhere else. If 3i Atlas were beaming towards some destination and Earth simply isn't in the beam path, we could listen for a lifetime and hear nothing. We'd be standing outside a lighthouse sweep, staring into darkness, concluding there is no light at all. History gives us missed signal lessons that should keep us humble. Pulsars, for example, to emit radio pulses like cosmic lighthouses, and we only discovered them because a few happened to sweep their beams across Earth. Before that, we were presumably bathed in silence from thousands of pulsars whose beams never touch our direction. Fast radio bursts went unnoticed for decades, despite being absurdly powerful, simply because no one knew to look for millisecond duration flashes buried in telescope data. We recorded them, archived them, and filtered them out as noise. Once we learned what to search for, we found them everywhere. We realized they'd been happening all along while we were calling the sky quiet. These examples don't prove 3i Atlas is transmitting in ways we can't detect. They prove something subtler. Negative results are always conditional on your methods. Silence in one frame doesn't guarantee silence in all frames. So why do intelligence agencies default to partial observability when scientists often don't? Because scientists work from completed observations, what the instruments actually measured, while analysts assume crucial data might be missing, hidden, or deliberately obscured. A scientist sees a 5-hour null result and correctly concludes no signal was detected in those 5 hours across those frequencies. An intelligence analyst sees the same null and asks different questions. What if it transmits outside our band? What if it transmits during the 19 hours we weren't listening? What if it beams directionally and we're not in the path? What if it uses modulation we don't recognize? The scientists Conclusion is epistemically sound for did we detect anything? The analyst's questions are strategically sound for could we be missing something that matters? Can we rule out anything? Confidently, yes. Some things. None of this means we should dismiss breakthrough listen or pretend the findings don't matter. They matter a great deal. They shrink the possibility space, ruling out broad categories of obvious transmission behavior and telling us that if 3i Atlas is artificial and transmitting, it would likely be doing so in ways that don't match our default expectations. That's useful. It makes some scenarios less plausible and others more plausible, but it doesn't close the book. It doesn't deliver the kind of total, all-frequency, all-time negative result that would let the mind fully relax. Radio silence isn't exoneration when silence can be explained by the limits of how, when, and where we listened. And when you're already dealing with an object showing multiple anomalies when the prior probability of weirdness has been raised by other observations, a negative result in one domain doesn't automatically erase open questions in another. The radio quiet leans toward natural origin, the geometric alignment, the nickel ratio, the sunward jet. Those lean towards something here still needs explaining. How you weight those pieces depends on whether you're trying to publish a careful paper or prevent a disaster. And whether you can discuss those weightings openly may depend on whether doing so reveals classified information about intelligence sources and methods. Which brings us to someone who did choose to discuss them anyway. Part 8, Avi Loeb and the institutional allergy. Avi Loeb is a theoretical physicist and astronomer at Harvard who has spent the last several years making his colleagues deeply uncomfortable. When Oumuamua passed through our solar system in 2017, most astronomers did what they're trained to do, propose natural explanations for unusual data. Loeb looked at the same evidence and argued we should seriously consider the possibility it might be artificial. That suggestion instantly made him controversial, not because he claimed certain proof, not because he abandoned rigor, but because he stepped over an unwritten boundary about which questions are acceptable in professional space science. You can speculate about exotic physics, dark matter, dark energy, quantum foam, the multiverse, but speculate about alien artifacts, and some peers begin to treat you like you've lost your grip. Loeb's sin wasn't being wrong, it was being willing to say out loud what many scientists think quietly, but won't touch in public. The stigma around serious discussion of technosignatures, artifacts instead of organisms, engineering instead of mere biology, is so strong that careers can take damage simply for asking the question. And that stigma didn't appear from nowhere. It's a defensive scar formed by decades of UFO noise conspiracy spirals, blurry photos, and dramatic claims every time someone can't explain a light in the sky. Science built walls around the topic to protect credibility with the public and with funding agencies. Those walls do work. They keep out a lot of garbage. They also, sometimes, keep out legitimate questions when those questions sound like the kind fringe voices ask. In 2025, Loeb proposed what he called a classification scale, a framework for rating interstellar objects by observed characteristics rather than assumptions about origin. The scale runs from natural objects with well-understood properties on one end to objects with characteristics inconsistent with natural formation on the other, with gradations of anomaly in between. It separates the question, what properties does this object have, from what should we conclude from those properties? You can place an object on the scale using observational data alone without claiming aliens, intelligence, or fabrication. The goal is a shared language for degrees of weirdness that doesn't instantly trigger the institutional allergy to fringe topics. Why make such a scale? Because without it, discussions polarize. One camp insists everything is natural unless proven otherwise. The other insists anomalies are proof. Both stances are understandable, but neither leaves room for the nuanced middle ground where real investigation usually lives. The scale offers that middle ground. It lets researchers say, calmly, this object scores high on anomaly and deserves closer study, without committing to any single explanation. It's a way to manage uncertainty systematically. Instead of declaring certainty too early, academia's incentives lean hard toward conservative interpretations. Publish a natural explanation and you're a responsible scientist. Publish an artificial hypothesis and you risk being labeled a sensationalist, making future publication harder no matter how solid your work is. That asymmetry nudges us to undervalue evidence for unusual hypotheses and overvalue evidence for conventional ones, not because of a conspiracy, but because of rational career survival. Junior researchers especially can't afford to attach their names to topics that might poison tenure prospects. Senior researchers have more freedom, but still face pressure to maintain respectability. The result is an environment where some questions don't get asked as loudly as they should, and some lines of inquiry remain underfunded and under-discussed, simply because talking about them carries social cost. Intelligence agencies run on different incentives. Their reputational risk comes from missing threats, not from investigating false alarms. If they spend resources on an unusual interstellar object and it turns out to be natural, almost nobody outside the building ever knows. No headlines, no public embarrassment. But if they ignore an unusual object because it seems ridiculous and it turns out to be something they should have taken seriously, people can die. Adversaries can gain advantage. And the agency faces the brutal question, why did you drop the ball? That flips the incentive structure. Academic caution can look like intelligence recklessness. The conservative interpretation that protects a scientist's career can become the risky interpretation that ends an analyst's career. And there's something interesting you can track in the language around 3I Atlas. If you watch closely. In Midway 2025, when the object was first detected and described, press releases used phrases like typical interstellar visitor, consistent with natural origin, no evidence of unusual properties. By late 2025, as observations accumulated, the language softened. Papers began to say requires further study, not fully explained by standard models. Interesting challenges to conventional understanding. The conclusions didn't flip. Scientists still leaned natural, but their confidence dipped in a way you could feel between the lines. Something about the growing dataset made simple dismissal less comfortable, and made researchers more willing to admit something unusual may be happening, even if we can't yet name it. Some of those discussions moved behind closed doors, conferences with preliminary results, funding panels, private conversations among colleagues who trust each other enough to speculate without public consequences. That's normal. That's how science breathes. You test ideas informally before you commit them to print. But there's a difference between ordinary caution and an unusual reluctance to discuss certain topics at all. Multiple researchers working on 3I Atlas have been quiet in ways that don't match their typical publication rhythms. Papers that seemed imminent haven't appeared. Conference talks that were announced were pulled. Maybe it's ordinary delay. Maybe initial results were wrong and someone wisely backed away. Or maybe someone suggested certain findings should be discussed in classified settings first, so intelligence agencies could assess what's being discovered before it becomes public. The shift from ridicule to silence matters. Ridicule says, "We checked, this isn't worth serious attention." Silence says, "We're not discussing this publicly." Both can be responses to weak ideas that don't deserve oxygen, but they feel different. When Loeb first floated the possibility that Oumuamua might be artificial, the response was fast and openly dismissive. Papers, debunkings, public statements. With 3I Atlas, there's been less ridicule and more quiet, fewer public debates, fewer definitive declarations, more watching and waiting without a clear explanation of what exactly everyone is waiting for. That quiet could mean nothing. It could mean the work is still preliminary and scientists are being appropriately careful, or it could mean the research found something that someone decided should remain non-public for now. Part 9. The Trojan Horse Hypothesis. Jupiter's Hill radius defines the region where Jupiter's gravity dominates the Sun's, its vast gravitational territory. Inside that radius, objects can orbit Jupiter. Outside it, objects mainly orbit the Sun. The radius extends roughly 0.3 astronomical units from Jupiter's center, an enormous spherical volume of influence. And it matters for anyone thinking about efficient travel through the solar system. Because Jupiter's mass can provide free acceleration gravity assists that sling a craft outward or inward without burning fuel. Every deep space probe humanity has sent to the outer solar system has used Jupiter this way. It's not optional. It's effectively mandatory unless you bring impossibly large rockets. Now look at 3I Atlas's trajectory. It moved through regions where Jupiter's gravitational influence is significant, where an object could use that mass to alter course, tweak speed, shift orbital parameters, all without active propulsion. That is exactly what a spacecraft would do if it wanted to explore efficiently, using gravity assists to reach multiple destinations on one pass. The trajectory isn't proof, because natural objects also get deflected, accelerated, decelerated by Jupiter under pure Newtonian mechanics. But it is consistent with what you might design for a multi-target observation mission, maximizing time near interesting places while minimizing fuel cost. Here's where speculation steps into territory that makes scientists uneasy, but keeps intelligence analysts awake. What if 3I Atlas isn't a single object? What if it's a carrier housing smaller payloads that could be released at strategic locations as it crosses the system? You'd build something like that if you wanted multiple observation posts, without multiple interstellar journeys, one large traveler between stars. Then smaller units deployed along the way. Those smaller units would be far harder to detect. They could observe passively to avoid revealing themselves. They could remain dormant for years, then activate when their design requires. This is the Trojan horse hypothesis. And it's vital to understand what it is and what it isn't. It isn't a claim that this is happening. It isn't evidence of deployed payloads. It isn't a conclusion drawn from public data. It's a scenario intelligence agencies feel compelled to consider. Because failing to consider it could be catastrophic if it were true. The hypothesis asks if someone wanted to study our solar system covertly. How might they do it? And an object like 3I Atlas would be an efficient answer. That doesn't make it likely. It doesn't make it believable without evidence. It only means we can't dismiss it outright when we already have an object showing multiple unexplained characteristics. Fragment release might be invisible to our current capabilities. Small objects, even a few meters across, are nearly impossible to spot against the background unless they emit or reflect light toward our telescopes at exactly the right time. If you wanted to deploy monitoring packages without being noticed, you'd release them on the far side of the trajectory relative to Earth. You'd time it for poor observing conditions. You'd make them non-reflective and radio quiet until needed. By the time we noticed anything, if we ever did, the carrier would be long gone, leaving behind quiet units with no obvious breadcrumb trail back to their origin. Or maybe nothing was deployed at all. Maybe 3I Atlas is simply a passive observation platform, a reconnaissance pass designed to gather data without interfering with the system being observed. You send a probe to study an active star system. You don't announce yourself. You watch quietly. You record. You continue on. No deployment required. No artifacts left behind. Just silent sensors drinking in information during the brief window when the trajectory crosses interesting regions. From our perspective, passive observation looks indistinguishable from natural behavior. No transmissions to detect. No deployment events to catch. No obvious signatures, just an object following a ballistic path, like any comet or asteroid we've ever tracked. So why is waiting scarier than acting? From an intelligence standpoint, because once an object leaves our solar system, we lose the ability to study it further, lose the chance to gather data that might resolve uncertainty. If 3I Atlas is a comet, waiting is fine. It departs. We learn what we can. We log it as another interstellar visitor and move on. But if it's something else, if there's any chance it deployed something, left something behind, or altered anything during passage, then waiting until it's gone means we can't investigate those possibilities. Can't determine what happened. We can't prepare for what might happen next. Departure is irreversible. And that irreversibility biases you toward investigating, now acting on incomplete information rather than gambling on complete information that may never come. There's no direct evidence for this hypothesis. We haven't detected deployed fragments. We haven't observed deployment events. We have no proof 3I Atlas carried payloads or released anything or did anything beyond following gravity's script. What we do have is a scenario that could explain why an intelligence agency might treat the object as operationally sensitive, why public reassurance and private concern might coexist inside the same government. The Trojan horse hypothesis is a thought experiment. Can the observed anomalies be arranged into a coherent narrative involving intelligence rather than pure natural process? The answer is yes, they could fit. That doesn't make the narrative true. It only makes it one possibility among several. And intelligence agencies have to assume something when they can't rule out everything. They can't operate on the comforting belief that unlikely scenarios never happen because their entire job is preparing for unlikely scenarios that would be catastrophic if they did. So they run possibilities. They model consequences. They ask what it would mean if the improbable turned out to be real. Sometimes that leads to embarrassing overreactions, resources spent on threats that never materialize, while other threats go unseen. But more often it leads to competent risk management, unlikely dangers monitored quietly. Preparation that costs little, acting as insurance against disaster. A high false alarm rate can be acceptable because the one true alarm you catch justifies the 99 you investigated. The question isn't whether the Trojan horse hypothesis is likely. The question is whether it's plausible enough to warrant classified monitoring, and if the answer is yes, that might explain a Glomar response better than any alternative we've touched so far. Part 10. Pascal's Wager for Planetary Defense. Blaise Pascal, a 17th century mathematician and philosopher, proposed a wager about belief in God that reaches far beyond theology. The logic goes like this: if God exists and you believe, you gain infinite reward. If God exists and you don't, you face infinite punishment. If God doesn't exist and you believe, you lose only the finite cost of belief. If God doesn't exist and you don't believe, you gain only the finite benefit of unbelief. Given those payoffs, the mathematically rational choice is belief because the expected value becomes dominated by the possibility of infinite consequence. The logic is coldly pragmatic, detached from faith or evidence. Focused on minimizing maximum regret, intelligence agencies apply the same structure to threat assessment. Even if they don't call it Pascal's wager, they call it worst-case analysis. Red teaming, contingency planning, different names, same mathematics, and the same quiet chill. If 3 Atlas is natural, and we treat it as natural, we commit only minimal resources, and everything resolves the way a quiet, ordinary comet story should. If 3 Atlas is natural and we treat it as potentially artificial, we still spend resources, we still chase a false alarm, and that cost is frustrating and wasteful, but it isn't catastrophic. If 3 Atlas is artificial and we treat it as natural, we risk missing the most significant event in human history. We fail to prepare for whatever consequences might follow, and we leave humanity exposed to scenarios we never seriously planned for. If 3-2 Atlas is artificial and we treat it as potentially artificial, we invest at a level proportionate to the stakes, maintaining readiness for outcomes that may never occur, but would be devastating if they did. That asymmetry in the payoffs drives intelligence behavior in ways that can look irrational to outside observers. Why spend time, money, and attention on unlikely scenarios? Because the unlikely scenarios that turn out to be real are the ones that kill people, end careers, and topple governments. Intelligence failures happen when agencies dismiss improbable threats that later materialize, not when they investigate improbable threats that turn out to be nothing at all. September 11th, Round 10. It looked improbable before it happened. So improbable that warnings were dismissed. So improbable that the idea of commercial aircraft as weapons wasn't taken seriously. Even with multiple intelligence reports sketching that exact shape of danger, after it happened, the failure became obvious. And the question everyone asked was why the warning signs weren't heeded when they seemed so clear in retrospect. October 7th, 2023 provides another example. Israeli intelligence received information suggesting Hamas was planning a large-scale attack. Information that felt improbable given the existing security situation. Information that didn't fit standard models of how Hamas typically operated. The warnings were noted, assessed, and ultimately dismissed as unlikely to represent a genuine threat. Then the attack happened, killing over 1,000 people and shattering assumptions about what adversaries were willing and able to do. In retrospect, the warning signs were there, waiting in plain sight. Intelligence agencies had access to information that could have prevented disaster if interpreted differently. But interpretation is always clouded by probability assessment, and by the need to focus limited resources on likely threats rather than spreading attention across every possible scenario, no matter how improbable it feels in the moment. These failures dominate threat modeling because false negatives, missed threats, are infinitely more costly than false positives. Investigated non-threats. A false positive costs money, time, and credibility when people learn you were chasing shadows. A false negative costs lives, infrastructure, national security, and political stability. The mathematics of consequence forces intelligence agencies toward high sensitivity, toward treating ambiguous signals as potential threats until proven otherwise, toward acting on incomplete information when waiting for complete information might mean waiting until it's too late to act effectively. That bias toward false positives is rational given the asymmetry of outcomes, even though it means most investigations lead nowhere. Most threats turn out to be misunderstandings, misinterpretations, or pure chance alignments of events that mean nothing. Secrecy reduces panic, a fact governments understand even when critics accuse them of authoritarian information control. Public discussion of potential catastrophic threats triggers predictable responses. Markets destabilize. People hoard resources. Social trust erodes. Political pressure forces hasty action that can make situations worse. Keeping threat assessment internal, classified, discussed only among people who need to know, allows for calmer analysis, more measured response, and preparation that doesn't create the very panic it's trying to prevent. This isn't always the right choice. Sometimes transparency is essential. Sometimes public input improves outcomes. Sometimes secrecy enables incompetence by shielding decision makers from accountability. But sometimes secrecy serves its stated purpose, allowing experts to work without interference, preventing escalation driven by fear rather than reason. How does silence stabilize systems? By preventing feedback loops where concern amplifies concern, where speculation becomes self-fulfilling prophecy, where the mere discussion of possibilities makes those possibilities more likely to occur through changed behavior. If you announce that an interstellar object might be artificial, you trigger massive public interest, political pressure to respond dramatically, calls for expensive monitoring programs, potential international conflicts over how to handle the situation. All of this ignites before you know whether the trigger was real or imaginary, before investigation produces actual answers, based purely on uncertainty that might resolve into nothing. So you stay quiet, you investigate quietly, you prepare quietly, and you speak up only when you have something definite to say. This approach minimizes disruption when threats turn out to be false alarms, while maintaining readiness if threats turn out to be real. Glomar responses buy time by deflecting questions without confirming or denying anything, by maintaining ambiguity that allows investigation to continue without triggering the cascade of consequences that acknowledgement would produce. If the CIA said, "Yes, we have records on 3 Atlas," they'd face immediate pressure to release those records, to explain why a space agency matter is an intelligence matter, to justify secrecy that conflicts with public statements from NASA. If they said, "No, we have no records," they'd be lying if records exist, opening themselves to legal consequences when the truth eventually emerged. The Glomar response avoids both problems by refusing to participate in the binary choice, by maintaining operational security through studied ambiguity that frustrates transparency advocates, but serves its purpose of protecting classified activities from premature disclosure. Act 2 has taken us from uncomfortable coincidences into uncomfortable questions about institutional behavior, about what happens when evidence doesn't quite rule out scenarios that seem absurd, about how governments handle uncertainty when the stakes might be existential. We still don't have proof of anything beyond the fact that someone thinks 3 Atlas warrants unusual secrecy, but we've explored why that secrecy might be justified even if the object is natural, why Pascal's wager logic applies to interstellar visitors as much as to theological questions, why certainty is not required for action when consequences are severe enough. The frameworks we've discussed: black swan theory, worst-case analysis, intelligence incentives, all point toward the same conclusion. When you don't know what something is, you prepare for what it might be. And you don't announce those preparations until you're ready to explain them. If 3 Atlas is a comet, this precaution looks like paranoid overreaction in retrospect. If it's something else, this precaution looks like basic due diligence, and we won't know which until someone decides to tell us. If they ever do, Part owns 2026's quiet rewrite of interstellar object protocols. Something changed in how astronomers categorize interstellar objects during late 2025 and early 2026. The shifts were subtle, invisible to anyone not following the technical literature closely. But they're there if you know where to look. Internal classification documents that previously divided objects into natural and artificial, with clear definitional boundaries, started using a third category. Anomalous natural. That phrase is doing a lot of work, trying to maintain scientific respectability while acknowledging that some objects don't fit neatly into conventional understanding. It's a linguistic compromise, a way of saying we think it's natural but can't fully explain it, without triggering the institutional allergies that come with suggesting anything might be artificial. The word unusual replaced impossible in multiple contexts. Papers that previously would have described certain observations as inconsistent with known natural processes now describe them as presenting challenges to current models, or requiring refinement of existing theory. This shift matters because it changes the epistemological status of anomalies. Impossible is a strong claim that something can't happen within our understanding of physics. Unusual is a weaker claim that something is rare or unexpected but not ruled out. By shifting from strong to weak language, the scientific community is admitting that their confidence levels have dropped, that accumulating observations are forcing them to be less certain about what is and isn't possible for natural objects to do. What's no longer ruled out? This list has grown longer recently. Multi-decade transit times through our solar system that previously seemed too long for cometary volatiles to remain active are now considered possible under certain exotic ice scenarios. Non-gravitational accelerations without visible outgassing are now explainable through multiple proposed mechanisms. Unusual chemical signatures are now attributable to formation environments we hadn't considered before. Each of these expansions of the possible serves to defend natural explanations against accumulating anomalies, preserving the conventional framework by making it more flexible. This flexibility is scientifically appropriate. We should update our models when observations don't match predictions, but it also raises the question of how flexible models can become before they stop making useful predictions, before natural but unusual becomes a catch-all explanation that doesn't actually explain anything. The difference between public and internal taxonomies reveals itself in how researchers talk about objects in different contexts. Public press releases emphasize how much we understand, how observations match expectations, how everything fits into conventional frameworks. Internal discussions at conferences and in private communications between researchers acknowledge more uncertainty, more discomfort with how well explanations actually fit. This isn't lying exactly, just emphasis management, presenting the most confident version of current understanding to non-expert audiences while expressing appropriate scientific caution among peers. But when the gap between public confidence and private uncertainty grows large enough, when the official story and the actual assessment diverge significantly, you're dealing with something beyond normal science communication challenges. Protocol changes often precede announcements because protocols are how institutions prepare for possibilities they're not yet ready to discuss publicly. If you're worried that future interstellar objects might exhibit characteristics that challenge current understanding, you rewrite your classification protocols to have categories ready for those characteristics when they appear. If you're concerned that some objects might require intelligence analysis alongside scientific analysis, you establish procedures for routing information to appropriate agencies before that need becomes urgent. These preparations are invisible to outsiders until suddenly they're invoked, until an object arrives that triggers the new protocols. And everyone wonders when those protocols were written and why. 3 Atlas fits into this institutional shift as the object that perhaps motivated it. Oumuamua started the conversation about how to handle interstellar visitors that don't behave exactly as expected. Borisov, The second confirmed interstellar object, reinforced natural explanations by behaving like a normal comet in most respects. 3. Atlas complicated things again by exhibiting multiple anomalies that resemble Oumuamua's strangeness, while technically remaining within the expanded boundaries of natural but unusual. The pattern suggests a slow learning process. Institutions updating their procedures as they encounter examples that stretch previous assumptions, but it also suggests preparation for something. A recognition that the category interstellar visitor might include members stranger than anyone anticipated, members that require new frameworks for understanding and new protocols for response. Pay attention to what gets reclassified in the coming months and years. Objects that were initially categorized one way then quietly move to different categories in updated databases without public explanation. Changes in how professional astronomical organizations define the boundary between natural and artificial, or between explained and unexplained. Shifts in funding priorities toward projects that can detect unusual characteristics in interstellar objects. These signals will tell us whether the scientific community is adapting normally to surprising observations or preparing for something specific, something they suspect might be coming based on what they've already seen. The quiet rewriting of protocols is either bureaucratic updating or institutional foreshadowing, and we won't know which until the next interstellar visitor arrives, and we see how these new protocols get applied. Part 2's AI discovering patterns humans were told not to see. Machine learning algorithms are discovering structures in astronomical data that human researchers don't know what to do with. This happens because AI approaches pattern recognition differently than humans do. Humans carry assumptions, filter observations through theoretical frameworks, see what they expect to see based on training and experience. Machines don't care about theory, don't worry about whether a pattern makes sense, don't suffer from confirmation bias or career concerns. They just find correlations in data, flag anomalies that deviate from learned norms, identify clusters that don't fit standard statistical distributions. Sometimes these flags represent instrumental errors or processing artifacts. Sometimes they represent real phenomena that humans missed because we weren't looking for them. In 2025, multiple research teams using different machine learning architectures to analyze archival, astronomical data reported similar findings. Non-random structures in the distribution of certain classes of objects, periodicities and signals that shouldn't be periodic, correlations between observables that have no obvious physical explanation. Each team published their findings cautiously, noting that the patterns could be artifacts of the algorithms themselves, that machine learning can find patterns in pure noise if you're not careful about validation. But when multiple independent teams using different methods find similar patterns, artifact explanation becomes less convincing. Something is in the data. Whether that something represents new astrophysics, measurement systematics, or processing errors, these results are being labeled unactionable in official responses, a designation that means no immediate research programs or theoretical work is recommended based on these findings. The justification is that without physical understanding of what's producing the patterns, without testable hypotheses about mechanism, the patterns are just curiosities rather than discoveries. This is methodologically sound. Science advances by understanding causes, not just documenting correlations. If you can't explain why a pattern exists, you can't predict when it will appear or how it will behave, and you can't build useful theory around it. So holding off on major research investments until the patterns can be connected to physical processes makes perfect sense from a resource allocation perspective. But there's another way to interpret unactionable. It can mean we recognize this is real but don't know what to do about it. Or this raises questions we're not prepared to answer. Or even this suggests possibilities we're not ready to pursue. Intelligence analysis uses similar language when sources provide information that seems credible but doesn't fit into existing operational frameworks. You don't dismiss the information. You don't act on it immediately. You table it pending further development while maintaining awareness that it might become relevant later. The parallel between scientific unactionable and intelligence unactionable is striking, both representing institutional uncertainty about how to process information that resists conventional interpretation. When patterns exist without explanations, the scientific response is to seek explanations through more research. Better instruments. Refined theory. The intelligence response is to monitor the patterns for changes, watch for connections to other anomalies, prepare contingencies in case the patterns indicate something requiring response. Both approaches are valid for their respective purposes. The question is whether 3 Atlas and similar interstellar objects are being subjected to both types of analysis simultaneously. Whether the patterns AI is finding in astronomical data are informing classified assessments alongside published research. If machine learning algorithms are flagging interstellar objects as anomalous, according to criteria humans didn't program explicitly. If the AI is seeing something in the data that doesn't match any conventional object category, that information has obvious implications for anyone trying to assess whether these objects might represent intelligence. The risk of suppressing AI findings is that humans might be filtering out real signals because those signals don't match expectations. We've done this before with conventional statistical analysis. Declared findings spurious because they contradicted accepted theory, and later discovered the findings were real and the theory was incomplete. Machine learning makes this filtering more perilous. Because we often can't explain why an AI reached a given conclusion, we can't trace the invisible path that produced its labels. If an AI says an object is anomalous but can't translate the reason into human terms, do you trust the warning or dismiss it as a black box whispering in equations? Intelligence agencies increasingly trust AI for exactly this kind of pattern recognition, using it to flag potential threats for human review. Except sometimes the machine sees patterns we can't articulate. Science is more cautious, insisting on understanding alongside detection, refusing to declare something real solely because an algorithm says so. The risk of amplifying AI findings is that you may end up chasing algorithmic mirages, spending resources investigating patterns that exist only inside the model's internal representation of the data, rather than in physical reality. This has happened in multiple scientific fields, most famously in genetics, where early machine learning studies reported disease associations that later turned out to be artifacts of population structure in the training data. The patterns were true in a narrow statistical sense, but they didn't reflect biological causation, leading to dead ends and wasted years. So scientific caution about AI-discovered patterns serves an important purpose, preventing premature conclusions based on methods we don't fully understand. But that same caution can become an excuse for not investigating patterns that make people uncomfortable, for shrugging off findings that hint at possibilities the institution isn't ready to hold in daylight. Part 3. The new solar system surveillance net. Space domain awareness, the military term for knowing what's happening in space, has expanded dramatically over the past 5 years. New sensor networks, upgraded ground-based telescopes, additional orbital monitoring platforms, all designed, ostensibly, to track satellites and debris, prevent collisions, and watch for adversary activities that might threaten space infrastructure. The official justification is entirely reasonable. Space is getting crowded. Commercial activity is accelerating. Nations are testing anti-satellite weapons. Collision risk is real and rising. We need better tracking to manage these hazards, to keep space usable for civilian and military purposes alike. Every major spacefaring nation is investing in these capabilities, building redundant observation webs that can detect smaller objects in more distant orbits. But these sensors are dual use by their nature. A system built to track satellites can track asteroids. A system built to spot debris can spot comets. A system built to monitor orbital space can monitor interstellar visitors drifting in from the dark between stars. The boundary between planetary defense, the civilian mission of protecting Earth from impacts and intelligence collection, the classified mission of assessing whether objects pose other kinds of threats, isn't always clean. The same hardware serves both purposes. The same data can feed both missions. Whether an object becomes a natural hazard or an intelligence concern often depends not on the photons themselves, but on interpretations made in classified rooms after the observations arrive. Coverage has increased, while transparency has decreased in ways that seem contradictory until you understand the dual-use logic. More telescopes scan the sky more often, finding more objects, building richer catalogues of our solar system's inhabitants. This gets celebrated publicly as scientific progress. as humanity mapping its cosmic neighborhood, but many detailed capabilities remain classified. The algorithms that process observations aren't published. The criteria for flagging objects for deeper scrutiny aren't revealed. So we know more is being watched, but we don't know exactly what's being found, or how decisions are being made about what gets announced versus what stays internal. Detection and disclosure are separate decisions. And that separation matters when you're tracking objects that might raise uncomfortable questions. Detecting an object is technical. Photons hit a sensor. Algorithms sift the signal. The object is catalogued with orbital parameters and physical characteristics. Disclosure is policy. A human choice. Someone deciding whether to announce the detection publicly, whether to include it in papers, whether to alert other observers, whether to classify the findings. Most detections are disclosed routinely because they're normal solar system objects requiring no special handling. Some detections are disclosed with delay, while observations are confirmed and refined, and some might not be disclosed at all if they trigger classification protocols designed to protect intelligence capabilities or to manage security concerns. Interstellar objects change surveillance priorities because they're a category that didn't used to command special attention. Before Oumuamua, interstellar visitors were a mathematical certainty. Objects ejected from other systems should occasionally pass through ours. But none had been definitively confirmed. The assumption was they'd be rare, and probably unremarkable when found. Interesting scientifically. Yes, but not demanding extraordinary resources. Oumuamua changed that assumption by being strange, by raising questions that simple observations couldn't settle, by making it clear that not every interstellar visitor would be a routine entry in an astronomical database. Since then, the emphasis on detecting and characterizing these objects early during approach, rather than after departure, has increased substantially. Multiple classified programs exist to track unusual objects in our solar system. This isn't speculation. It's an acknowledged fact that the Department of Defense operates space surveillance programs whose specific capabilities and findings remain classified for national security reasons. Some focus on foreign satellites, adversary space behavior, and deterring anti-satellite weapon tests. Others have broader mandates, monitoring all objects above certain thresholds regardless of origin or label. The existence of these programs means the government knows more about what's in space than what is publicly announced, has access to higher resolution data than most civilian astronomers can gather, and uses classification to control what reaches public awareness and what stays inside the intelligence community. When an interstellar object appears and shows unusual traits, it's likely being tracked by multiple overlapping systems. Civilian surveys funded by scientific agencies, military surveillance networks watching for threats to satellites, intelligence platforms built to characterize unknown objects with quiet precision. Data from these systems can yield different conclusions because they're optimized for different goals, using different sensors and different frameworks. A civilian astronomer sees spectra hinting at odd chemistry and thinks, interesting comet, warrants further study. A military analyst sees trajectory geometry that looks strategically tidy and thinks, potential reconnaissance platform, warrants threat assessment. An intelligence analyst sees both data streams plus classified context and thinks, something that can't be discussed publicly, because the integration itself would reveal what we can do and how we know. The surveillance net is tightening around our solar system in ways that will inevitably surface more anomalies, more objects that don't fit cleanly, more observations that ask unsettling questions about whether everything we see is purely natural. This is partly progress, better instruments finding what we couldn't see before, but it's also a response to specific concerns, the recognition that verification requires vigilance, that assuming innocence by default may be unacceptable when a single exception could matter. The new surveillance net is infrastructure built for possibilities that haven't been publicly acknowledged. Capabilities deployed in anticipation of scenarios that sound like science fiction, right up until the moment they don't. And the silence around these capabilities, the refusal to discuss their true scope, suggests those possibilities have risen from academic hypotheticals into operational priorities. Part 14. Another nothing to see here event from this year. In March 2026, a minor scientific controversy flared and was resolved so quickly most people never heard about it. A research team analyzing archived satellite data claimed evidence of periodic variations in Earth's ionosphere that didn't match any known natural or human-caused source. The variations were tiny, detectable only through sophisticated processing, appearing at regular intervals that didn't correlate with solar activity. Magnetic storms, or the usual drivers of ionospheric motion. Their initial paper offered several natural explanations, none fully satisfying, and called for additional observations to better characterize the phenomenon. Within days, a senior researcher at a major institution published a rebuttal arguing the signal was an artifact of the satellite data pipeline, calibration errors masquerading as structure, systematic bias dressed up as rhythm. The explanation was plausible, well documented, and supported by detailed analysis showing how instrumental effects could produce exactly the observed pattern. The original team withdrew their paper pending further work, acknowledged potential calibration oversights, and thanked colleagues for catching the issue. From the public perspective, the story ended neatly there. Science working as intended, a claim made, an error identified, a correction issued. Everyone drifting on to the next question. But here's the curious detail. The senior researcher who identified the calibration issue had no prior expertise in ionospheric physics, no publication trail in that area, no obvious reason to be fluent in the quirks of the specific satellite system involved. Their rebuttal arrived with remarkable speed, faster than typical peer review, using calibration details that usually take months to obtain through official channels. And the original team, when asked informally about the withdrawal, offered vague answers about ongoing discussions with instrument groups and potential security classifications of certain calibration specifics. None of this is definitive. All of it could be explained by ordinary scientific correction, but the pattern is familiar, an observation that doesn't fit. Rapid institutional pushback, quiet suppression via technical objections, and researchers backing away without a clean public explanation. This pattern appears across disciplines. When observations brush against phenomena institutions aren't ready to acknowledge. Anomalies get posted often in lower-tier journals or preprint servers, drawing brief specialist attention. Then senior figures publish confident counter-explanations that preserve the conventional frame. The original researchers either defend their result and risk being marginalized, or accept the correction, keep their careers intact, and watch the controversial finding fade into silence. The process is defensible as quality control, as seasoned expertise catching mistakes before they spread, but it can also be useful for burying inconvenient observations, for maintaining consensus against data that threatens it. Minimize, monitor, reframe. This is the institutional reflex when information is potentially important and definitely uncomfortable. First, minimize the finding. Treat it as likely error or misinterpretation. Discourage wide attention until more data arrives. Simultaneously, monitor internally. Pull additional information through channels that don't require public disclosure. Prepare for the possibility it might be real. If monitoring confirms error, reframe the episode as science working properly. If monitoring suggests it's real, reframe it as a newly discovered natural phenomenon requiring updated theory, or classify it as sensitive information requiring restricted access. Either way, the public story emphasizes confidence and control, never surprise. Why do anomalies age better than explanations? Because anomalies are observational facts, data points that remain, even when interpretations shift like sand. Explanations are the stories we build to hold the facts together. And stories can be wrong even when the facts are right. When an anomaly first appears, institutions rush to fit it inside existing frameworks, reassuring everyone that nothing fundamental has changed. We just need a minor tweak, a small correction, a gentle adjustment. But if the tweaks don't truly work, if the explanations require increasingly brittle assumptions, if each new observation makes the conventional story less convincing, then the anomaly outlasts its cover story. People remember that something strange was measured and forget the neat explanations that tried to erase it. And when anomalies accumulate faster than explanations can mature, institutions face a choice: admit current understanding is inadequate, or double down on narratives that start to resemble denial. 3 Atlas sits in this slow process of anomaly aging right now. At the moment, the conventional explanation still holds. It's a comet, an unusual one, stretching natural models without clearly breaking them. If no further strangeness appears, these oddities will be absorbed into refined comet theory, remembered as proof that nature has more variety than we expected. But if new observations strengthen the anomalies rather than dissolving them, if other interstellar visitors arrive with similar signatures, then we'll look back at this period and wonder why we worked so hard to sand down the edges. The anomaly will age into established fact. The explanations will age into historical curiosities, reminders of how institutions resist paradigm shifts, even as evidence gathers. And perhaps decades from now, researchers will ask why certain data was classified, why certain observations were softened, why the most straightforward interpretation was the last one anyone officially allowed themselves to consider. Pot Kings, white swan or black swan, we return to where we began, to the contradiction that opened this investigation. NASA calls it a comet. The CIA refuses to confirm or deny whether records exist. One agency says everything is normal routine. Understood. Another says that even acknowledging attention would reveal classified information. That contradiction hasn't been resolved. It's been explored, not answered, examined, not closed. And maybe that's fitting. Some contradictions don't resolve cleanly. They become facts we live with, border stones marking what we know, and what someone else knows but will not say. Let me summarize the anomalies without stacking them into conspiracy. 3 Atlas showed a sunward jet that persisted longer and stronger than conventional, outgassing models easily explain. Its rotation axis and orbital plane aligned with solar system geometry in ways precise enough to raise statistical eyebrows. Its chemical signature included nickel-to-iron ratios that resemble engineering alloy ranges more than typical comets. It passed within 9 degrees of the region where the WOW signal originated 48 years ago. Breakthrough Listen detected no radio signals during a 5-hour window. The object's trajectory carried it through Jupiter-influenced space, where deployment of smaller payloads would be efficient if deployment were intended. Each anomaly has natural explanations. Together, they create a pattern that some people find unsettling. The significance of the Glomar response can't be overstated, because it's the only part of this story that is definitively strange without interpretation. Everything else demands weighting, probability, judgment, how much you trust models versus how much you respect outliers. But the CIA letter is simply weird. No metaphors required. They could have said no records exist. They chose not to. And that choice reveals more than any telescope image. Because it was made by people with access to information. We don't have people whose job is to assess national security risk. People who decided this object warrants protection under the same legal framework used for spy satellites and covert operations. Maybe that decision is overreaction, institutional caution, running ahead of reality. Maybe it's appropriate restraint in the face of uncertainty. We can't know which unless they tell us. And the point of a Glomar response is that they won't. If nothing is happening, if 3 Atlas is simply a comet, and the anomalies and natural wrinkles will eventually smooth into better theory, then the secrecy is irrational. It accomplishes nothing except fueling suspicion, eroding trust, and casting the shadow of a cover-up where ordinary transparency might have let the night sky feel quiet again. No legitimate intelligence purpose is served by classifying a comet. No source is protected. No method is exposed. No operational edge is preserved. In that case, the secrecy looks less like strategy and more like institutional dysfunction. Agencies blurring the line between real secrets and routine data, a slow, quiet classification creep where everything gets stamped confidential by reflex, not necessity. That reading is unflattering, but not, by itself, terrifying. Bureaucracies make foolish calls all the time. But if something is happening, if there's any genuine reason to treat 3i Atlas as an intelligence problem, not just a scientific one, then secrecy becomes almost unavoidable. You don't announce to the world that you're tracking a potentially non-natural object while you're still trying to learn what it is and what it implies. You don't broadcast preliminary assessments that could be completely wrong and trigger panic or tilt delicate geopolitical balances. for nothing. You don't reveal which indicators you're using to separate natural from artificial, because the moment you publish your checklist, you teach others how to slip past it. In that frame, secrecy has a legitimate function. It protects the investigative room, the quiet time needed to test. Verify. Discard. It prevents premature disclosure of information that might prove meaningless or catastrophically consequential. That interpretation is unsettling, but it's also rational. So we're left with uncertainty, not fear. Fear is the body reacting to known danger. Uncertainty is the mind holding an unknown shape without flinching into certainty too soon. Fear would be appropriate if we knew Three-Eye Atlas was dangerous, if we had proof of threat demanding immediate action. We don't have that. What we have is a set of observations that don't quite lock together, explanations that fit one at a time but begin to strain when you stack them, and institutional behavior that implies someone, somewhere, has marked this as special. Uncertainty is the correct response to that geometry. To say, calmly, we don't know what's happening, and still notice the official narrative doesn't perfectly match the official behavior. The silence becomes the loudest signal because it's the only piece that is definitely intentional. Sunward jets might be natural, or might mean something else, but they are not produced to speak to us. Geometric alignment might be coincidence or optimization, but it isn't trying to send a message. A GLOMAR response is communication, a deliberate decision about what to share and what to withhold, a signal, stamped in legal language, that someone decided this crosses a classification threshold. When governments choose silence, when they refuse to confirm or deny instead of simply explaining, they are telling you something, even while refusing to say what. They're telling you that some aspect of this situation has crossed a line normal science communication doesn't cross, where intelligence concerns begin to outweigh transparency. I want to end not with answers, but with the recognition that some questions don't come with public answers. Not because answers don't exist, but because someone has decided we don't need them. That decision might be justified, serving protective purposes we'd support if we understood them. Or it might be unjustified, a cover for uncertainty and institutional clumsiness, not genuine secrets. From the outside, we can't reliably tell. We can't separate good secrecy from bad secrecy when we don't know what's being kept secret. So we make probabilistic judgments with partial information, deciding whether to trust the reassurance or trust our quiet recognition that the reassurance and the behavior don't fully agree. 3-Atlas is gone now, continuing into interstellar night, carrying whatever it carries beyond our reach. If it was only a comet, we studied it reasonably well, added a few more useful data points to our understanding, and moved on to the next curiosity. If it was something else, then we missed the moment when certainty could have been earned. We lost the chance to resolve the unknown while it was still observable, still close enough to touch with instruments. Either way, we're left with questions that will age better than the answers we were given, anomalies that can outlast tidy explanations, patterns that remain patterns, no matter how often we're told they're just coincidence. And somewhere in a classified facility, behind thick doors and quiet screens, someone knows more than they're saying, has access to data we will never see, and is shaping assessments that may never be declassified. The contradiction that opened this investigation remains a contradiction. The mystery remains mysterious, and the silence, that deliberate, calculated, legally protected silence, continues to be the clearest signal that something about this object matters more than anyone wants to admit. It